All right, I think it's time that we start working with Ethereum directly. One of the great things about a decentralized cryptocurrency is that we can connect directly to the network to submit transactions. Of course, to make a transaction, you have to have some currency to spend, which we don't have yet. Also, it can be a little daunting to try and learn Ethereum while we're spending money on a production network. When coding, we generally develop and test on our own machine before we deploy it to production. In Ethereum, we're going to do the same thing. We'll run a single Ethereum node on our own machine to make sure we understand how it works. Later, when we're confident in our code, then we'll deploy it into production. For now, let's boot a single private Ethereum node. That way we can test whatever we need without worrying about making mistakes. So let's download an Ethereum client, create some accounts, and then send some money between them. One of the first things to know about Ethereum is that it is a protocol. And that means that there are many possible clients that we could use. Think of it like this. We send and receive email by using SMTP and POP. You can use any client that you want to. I might use Gmail, you might use Apple Mail or Hotmail, but as long as all of the clients know how to speak the protocol, we can send and receive emails from each other. The same thing goes for HTTP. HTTP isn't owned by the HTTP company where they can just change the protocol at will to be whatever they want. Instead, HTTP is a defined protocol that we all just agree on. You can use whatever browser or code that you want to communicate to any other service that uses HTTP. In the same way, Ethereum itself is a protocol. In one sense, Ethereum is just whatever we all agree it to be. And this idea of consensus, defining the rules by which we all agree on something, it comes up all the time in the blockchain space. But for now, the practical implication is that we have several different Ethereum clients we can choose from. We're going to be using Go Ethereum, or Geth for short. It's the official Go implementation of the Ethereum protocol. And again, you could use any client you want, and you could even implement your own. But Geth is the most popular, so that's what we're going to use. To download Geth, head on over to the download page and download the binary for your system. When you unzip it, you should have a binary named Geth, which you need to save somewhere. So I'm going to make a new directory, courses newline Web3, and I'm going to make a bin directory and copy Geth into it. Now that we have Geth, we need to do some initial configuration. For our private node, we are not joining the production Ethereum network. We're not going to download the history of everything that has happened in the Ethereum network this far. Instead, we're going to start our own private network. We're going to start with a clean slate. This clean slate means that we are creating our own blockchain. I know that we haven't talked about what a blockchain is or how it works, but we will. For now, just think of it like your test database and your production database. You can't just merge your test database into your production database and expect it to work. Similarly, changes to our local Ethereum blockchain will have no effect on the production Ethereum network. We're going to configure our local test blockchain by using this configuration file, genesis.json. You can get a copy of this file from the lesson notes. Each of these configuration parameters will make sense in time, but for now, just copy this file and save it as genesis.json. When we boot Geth, it's going to save its database in a folder on our disk. This folder saves the state of our blockchain, and more importantly, the keys to our accounts. We will specify this folder every time we boot our Geth node. Let's initialize our node now. I'm going to type ./bin/geth, datadir equals datadir, init, and pass the genesis.json. So I can ls this folder, and look what's inside datadir. We can see that datadir was created for us and it contains two folders, Geth and keystore. The Geth directory holds our blockchain data. The keystore directory will hold our account keys once we have them. Geth contains a number of commands and options. We can see the list by running --help. One of the first things we're going to need are accounts. We can create an account like so. /bin/geth, datadir equals datadir, account new. We're going to need this password later, so I'm just going to use the password ABC123. Obviously, you need to use a strong password when you start handling real funds. Notice that when we created this account, it output an address, which is a long string of characters. This is your receiving address, and it's okay for it to be shared publicly. We can now see that address in our list of accounts by calling accounts list. Now if we look at the datadir, you can see that we have a new file in the keystore. We can cat that file out. But that's not very clear to look at, so I'm going to pipe it through a tool JQ for readability. Here's our address and a variety of other parameters. While the address can be publicly shared, the rest of it needs to remain secret. If someone had the information in this file, they would be able to steal all of the Ethereum controlled by this account. There's another important and interesting thing that you should know about accounts. They're generated completely offline. For comparison, when you create an account with Facebook, you hit Facebook's servers and they'll create an account in their database which you can use. And similarly, when you create a traditional bank account, you go to your bank, you prove your identity, and you ask them to create an account for you. They create an account in their database and they let you use it. Ethereum accounts, and Bitcoin too, are generated from an algorithm, completely offline. You're not hitting a remote server to generate this address. In fact, no one knows that this address even exists until it's part of a transaction in the network. In one sense, you're just picking an address at random out of a huge pool of possible addresses. If you're familiar with SSH, it's a lot like generating SSH keys. You don't ask for permission from a central server to generate an SSH key. You generate it from randomness and an algorithm on your computer. So you can generate as many addresses as you need. Just make sure that you securely back up your private keys. Now that we have an account, let's play with it. So far we've been running Geth commands from our shell, but Geth actually comes with a console of its own. We can run this with the console command. This console is a JavaScript console. That means we can write functions, perform calculations, etc. There are also a number of libraries pre-installed that we can use to interact with Ethereum. The first one is simply called ETH. We can view our list of accounts like this, eth.accounts. Ether is the currency of Ethereum. If we want to find out how much Ether we have, we call eth.getBalance. So here we call eth.getBalance, and then we paste in the address of our account. We don't have any Ether yet, so it just says 0. And this brings up an interesting question. Where does Ether come from in the first place? Ether is created as a reward for mining blocks. Again, we'll talk later about how mining works technically, but loosely, when we want to send Ether to someone else, we create a transaction, and these transactions are grouped into blocks. Miners verify that these blocks are valid, and then they are rewarded Ether for doing this. The key idea is this: the Ether is created out of thin air. This is another example of consensus. We all just agree that miners get to create Ether to give themselves a reward for doing their job. So here, we can get Ether by being a miner ourselves. To do this, we'll call miner.start. We pass the number of threads, in this case, it'll just be 1. Now, when you call this, you might need to wait a few seconds, maybe even a minute, before you see successfully sealed a new block. But let it run for a bit, just wait. And then after a few blocks, stop the miner. You can find out the number of blocks we mined by calling eth.blockNumber. Every block we mined will have earned us a certain number of Ether as a reward. This reward will go to the account address we set up earlier. And note that your mining destination address is sometimes called your Etherbase address. Let's find out how much Ether we earned. First, let's look up our accounts. And because this is JavaScript, we can also do this. Now, instead of copying and pasting our address, we can use that in getBalance. Well, you can see this is a large number. What we're actually seeing here is the number of Wei we earned. Ether has a bunch of different units, with Wei being the smallest. Wei is sort of like cents are to dollars, except that 1 Ether is 10 to the 18th Wei. You can view the whole list of the units here, but we're only going to be using Wei and Ether. It would be nice if we could see this number in Ether instead of Wei, and thankfully we can use the fromWei method to do this. The fromWei method is in the Web3 library, so we type web3.fromWei, we put in our account address, and then the unit we want, which is Ether. Much better. Now we can see that we earned 20 Ether for mining the last few blocks. Now that we have some Ether, let's spend it. If we're going to spend some Ether, we need to have someone to send it to. But right now we only have one account. We could create a new account by using the Geth command line like we did earlier. But we can also create an account from here. We do that by calling personal new account and then passing the password for that account. I'm going to use the same password as last time, ABC123. Now let's check our list of accounts. Great, now let's check the balances between them. So in this first account, we have Ether because that's the account we sent our mining rewards to. But in the second account, we don't have anything. To send Ether from one account to another, we need to specify the from address, the to address, and the value of the transaction. We'll do this with the send transaction method. We'll type eth.sendTransaction from eth account 0 to eth accounts 1, and the value will be 3 Ether. Uh-oh, we got an error. It says authentication needed. Why is this? Well, it's because our from address is locked. This is a security mechanism to prevent you from sending funds when you didn't intend to. Let's unlock our sending account and then try sending the funds again. We'll call personal.unlockaccount, pass our address, and then our password. Now we can try sending our transaction again. I'm hitting my up arrow here to search my history and find the code earlier that we used to send a transaction. Great! This says submitted transaction and it returned a hash. This hash is the identifier of our transaction. Let's look at it more closely. We can do that by calling eth.getTransaction and then passing the hash. Take a look at the to and the from fields. You'll notice that these match our account addresses. Also, the value field is the value we were sending denominated in Wei. Since we submitted a transaction sending 3 Ether from one account to another, our balances should have changed, right? Well, let's check. We'll call eth.getBalance on account 0 and eth.getBalance on accounts 1. It looks the same as before. Why is that? Well, it's because even though we submitted a transaction, they haven't been included in a block that was processed by the miners. Take a look at the information returned by getTransaction again. Notice that the block number says null and the block hash is just 0. This transaction hasn't been included in any block, so our account balances haven't changed. In order to process this transaction, we need our miners to include it in a block. We can do that by starting our miner again. Here we'll call miner start and wait a few seconds. Wait for a few blocks to mine, and then call miner.stop. Notice in our miner debug log that the transactions equals 1. This is saying that this particular block has 1 transaction. And notice that the rest of the transaction numbers are 0, and that's because we haven't been submitting any other transactions, but the miner will still mine the empty blocks just to get the reward. Now let's try checking our balances again. This time we'll get it denominated in Ether. Well, with account 0, it's hard to tell if that worked because this is our Ether-based account. So it's earned rewards while we were mining. Let's check the destination address. Great, it has 3 Ether in that account, so our transaction worked. Let's take a look at our transaction hash again. Notice that we now have a block number as well as a block hash. We can also take a closer look at the block this transaction was included in by using eth.getBlock. There's a lot of data in here that will make more sense as we get further along, but take a look at the array of transactions and notice that it contains our transactions hash. Each block stores a reference to its parent block, and we could look up the parent block by using the parent hash. And if we looked at parent hash, we would see a list of transactions there, and then we could look at its parent and so on all the way back to the original Genesis block. This idea of a block being parented by another block is the chain part of a blockchain. Every transaction that has ever happened in Ethereum can be found this way. While it's exciting to send value from one account to another through a decentralized network, Ethereum can do so much more. What makes Ethereum so special is that we can write programs that will handle this value for us. And that's what we're going to take a look at next. So you might be asking, what is a smart contract? And the answer is, it's like a regular contract, but defined by code. But let's take a step back. What is a contract anyway? Normally when we think of contracts, we think of a piece of paper where you sign on the dotted line, but the idea of a contract is a lot more general than that. Fundamentally, a contract is an agreement between two parties, and we agree on and participate in contracts all the time. Maybe it's an agreement to buy a car and pay the lender every month. Or maybe we'll make an agreement with our library that we can borrow a book and we'll return it on time or else we'll pay a fee of 10 cents per day. Maybe it's an agreement to pay monthly for fire insurance, and if our house burns down, the insurance company agrees to pay us a lump sum. Or maybe we have an implicit social contract with our friends that when we go to dinner, we'll all split the bill evenly. Another place where contracts are used extensively is financial products. Stocks are a good example of this. Owning shares in a business gives you certain rights as a shareholder. You might receive a portion of the business's profits through dividends, have access to their financials, or hold certain voting rights, etc. These rights are defined by a company's shareholders' agreement, which itself is shaped by the governing laws in a particular jurisdiction. And even then, enforcement of any particular clause depends on the lawyers and judges and lawmakers involved. The idea with a smart contract is that we're totally defining the rules of our agreement in code. We should look at some examples. Nick Szabo, the inventor of BitGold, developed the concept of smart contracts. In his essay titled The Idea of Smart Contracts, he gives two examples. One, the idea of a vending machine, and two, a car loan with a twist. Let's start with a vending machine. You can think of a vending machine as a mechanical contract between a thirsty buyer and a beverage manufacturer. The buyer puts in a certain amount of money, and the machine dispenses a drink and change if necessary. There's even a rollback mechanism if the buyer requests a refund or the drink can't be delivered. The vending machine acts as an escrow between the buyer and the seller. And although what's at stake is small, there is a moment where the vending machine controls both the drink and the funds. The buyer and seller both agree to this arrangement because there's an understanding that the machine will act according to its programming and treat both sides fairly. Of course, one weakness of the vending machine metaphor is that the vending machine is controlled by the drink manufacturer, which as a buyer means that there is a chance that the machine will cheat you by taking your money and not dispensing a drink. In smart contracts, however, this asymmetry of trust can be removed. That is, in the ideal smart contract, there's no scenario where one party can defraud the other. You can't inspect the code of your vending machine, but you can inspect the code, or at least the proofs, of your smart contracts. Another example Szabo gives is the idea of a car loan. But in this case, the keys to the car are cryptographic keys, and these keys are initially controlled by the smart contract. The idea is that the terms of the loan are encoded in the smart contract, and the contract gives control of the car to whoever rightly owns it. For instance, the buyer needs to make payments each month, and if he pays on time, he keeps control of the car. However, if the buyer were to fall far behind on his payments, the smart contract would automatically return control of the keys to the lender. On the other hand, if the buyer keeps his payment schedule, when the loan balance is paid off, the smart contract will return control of the car to him irrevocably. That is, the smart contract would permanently, cryptographically, give control of the keys to the car to the buyer. To generalize, the key idea here is that any property which can be represented digitally can be managed in code with smart contracts. Another way to view smart contracts is as a board game. When you and I agree to play chess, we're agreeing to a specific set of rules, such as the board will have 64 spaces, or a pawn can move 2 spaces on his first turn. We can model chess in a smart contract, and then sit down and play the game. Any move made within this game must abide by the rules. And conversely, any move that's within the defined rules is permissible. When we agree to abide by a contract in code, whatever is logically valid within that code, that's what we'll hold to no matter what. However, a problem with this approach is that many contracts are a lot more open-ended than the rules of chess, and it can be very difficult to define every possible outcome. Traditional contract law is dynamic and has been refined through thousands of years, and this means it can remain robust in the face of complex and ambiguous situations. Nick Szabo is fond of saying that a contract is a program that runs on the brains of lawyers. And the upside is that these brains are very sophisticated, but the downside is that these human executions are non-deterministic. And this idea of contracts as a program is really at the heart of what we're trying to do. When we talk about smart contracts, it's really just code. In Bitcoin, a smart contract might be something as simple as a list of operations that check for a required number of signatures. In Ethereum with Solidity, a smart contract is essentially an instance of an object. Our vending machine, for example, could be a smart contract. From a programmer's perspective, this vending machine smart contract code is an object. It holds its own state variables, such as the current inventory of the sodas, and it also has methods which can read and write that state. It's early days for smart contracts, and the scope of what contracts can be written in code remains to be seen. But we now have the tools to start experimenting in code on production decentralized systems. Let's start writing a smart contract in code. Let's write and deploy our first Ethereum smart contract. The process looks like this. We'll write our contract in a high-level language. Next, we'll compile it. Then we'll deploy it to the network. And after it's been deployed, we can interact with it. In order to write contracts on Ethereum, it's really important to understand the context in which they are run. The first thing that we'll start with is the Ethereum virtual machine, or the EVM for short. The EVM is a low-level, assembly-like programming environment. It can perform arbitrary computations, put data in storage, read that data out, etc. When we write code for Ethereum, we generally don't write the bytecode directly. Instead, we use a higher-level language that compiles down to these basic operations. The second thing to know is that this code is run by every node on the network. That is, every minor node on the Ethereum network will run our smart contracts code. But keep in mind they're going to run the EVM bytecode and not our Solidity code directly. Because our code is run by every node on the network, this has a lot of implications around data privacy and cost. We'll talk about those later. The third thing to keep in mind is that our contracts will only run in response to a transaction. That is, they're not running constantly in the background. Instead, our contracts will only run and make changes if a transaction is sent to the network that wakes them up. There's a lot to unpack here, so let's just start by looking at some code. I'm going to be working out of our newline Web3 directory. I'm going to make a contracts directory, and I'm going to create the file contracts_counter.sol. You can find this in the lesson notes. This is a Solidity contract. It keeps track of a count variable, which we can increment. Now, it's not the most exciting code, but we have a lot of new ideas to cover around Ethereum itself, and we'll expand into more interesting contracts once we grasp how everything fits together. We open by stating pragma solidity and then a version number. This pragma is an instruction to the compiler as to what version of Solidity we're using. The version number is semantic versioning, much like JavaScript's NPM modules. The version number is important because, remember, we're not running Solidity code on the EVM, we're running bytecode. The Solidity compiler compiles this contract down to EVM bytecode. The Solidity compiler, like the rest of the system, is under development, and so two different versions of the compiler could reasonably emit two different versions of the bytecode. This might not be that important when we're compiling code for a regular computer, but when our code is controlling thousands or sometimes millions of dollars, little changes in the compiler can make a big difference. So we fix our Solidity version in our smart contract, so that way we know we can get a consistent output from our code down the line. Next, we define our contract with the keyword contract, as well as the name of the contract, which in this case is counter. A quick scan of this code might remind you of JavaScript. And that's deliberate in that Solidity was designed to be approachable for web developers. That said, don't let the superficial similarities fool you. Solidity is just similar enough to JavaScript to be dangerous. There are some unintuitive aspects of Solidity that you really have to be careful of. We'll cover them as we go along. But one similarity is that you can think of this contract as a class. The counter contract is like an object class. On the next line, we have uint count. Solidity is a statically typed language, and this count variable is an unsigned integer. Uint is an alias for uint256, which means it can hold a positive integer up to 2 to the 256th minus 1. It's a very large number. The value of this counter will be stored on the Ethereum blockchain. This means that the value of count will be stored on every full node on the Ethereum network. This service is not provided for free. If you want a value to be stored permanently by thousands of nodes, you're going to have to pay for this. Understanding and calculating these costs is also something we'll talk about later. For now, know that this count variable is like an instance variable. We can read from it and write to it, as you see in the functions below. The first function that we have is the constructor. The constructor is a function with the same name as the class. As happens in other languages, the constructor function is called when we create an instance of the class. One question you might be asking is, how do we create an instance of this class anyway? The answer is, after we compile the code, we'll submit a transaction to the network that creates an instance of this class. This instance will be given its own address, and it can control both data and funds on the Ethereum network. That is, this contract can receive payments of its own, it can verify conditions, and it can send funds out. Well, this counter contract can't do any of that because we haven't implemented any of that functionality. But in other contracts, we will. Just know that when we upload this code to the network, an instance will be created and given its own permanent immutable address. Speaking of immutability, another thing that you should know is that once we've created an instance of a contract, its code is immutable and cannot be changed. You can't upload a bug fix and you can't make any tweaks. Once it's been created, it's written in stone. There are strategies for mitigating this limitation, but really immutability is a feature, not a bug. But you'd better make sure that you do extensive testing before you start handling real funds. Back to our code, in this constructor, we're going to set count equal to 1 when the contract is created. The next function is increment. The increment function will read the existing count from storage, add 1, and then store the new value in the count instance variable. The get function returns the value of count. In the get function declaration, we're stating that it is a constant function, which means it doesn't modify any of the state, and it returns a uint, an unsigned integer. Remember, every node on the network stores a copy of the storage for every contract. And given that we have our own node, this means that we can read any of the data for free instantly. That is, the get function can be executed completely on our local machine without going to the network. We already have the value of count on our disk. The increment function, however, is different. Because it changes state, the validity of that change must be confirmed by the whole network. So to make a call to increment, we must submit a transaction that calls increment. That transaction will hopefully be picked up by a miner to be included in a block. When that happens, the transaction will be run, which will increment the count value. We've looked close enough at this code, let's compile it, deploy it, and then interact with it on the blockchain. To compile our Solidity smart contract, we need a compiler. The main Solidity compiler is Solk. It's written in C++, and it's a good idea to use a formal release build for your production smart contracts. That said, getting the C++ version of Solk installed can sometimes be a pain. My recommendation is that you install Solk before you deploy your first smart contracts to the production network, but for now, we can just use the JavaScript version Solk.js. To install Solk.js, we'll run npm install-g Solk. Remember, this installs Solk.js, not the C++ version. Solk.js's core code is generated using mscripten, which converts the C++ version of Solk into JavaScript. This means it'll work just fine. It's a little slow, but know that the command line options are different. There are other IDE-like tools we can use to compile our contracts, and we'll look at those. But since we're just getting started, I think it's clearest to just compile them by hand ourselves on the command line. We can compile our contract by typing this, solkjs-bin counter.sol. Let's take a look at the output. Well, that's not exactly enlightening, but this is a hex-encoded version of the bytecode of our script. There are other ways of viewing the opcodes that are clearer, but we don't need them right now. While we're here, another thing we need to generate is the ABI, which stands for Application Binary Interface. The ABI defines the interface to the functions on our contract. The reason we need this is because the encoding of our program is not self-describing. That is, you can't easily tell from the bytecode how each function should be called or what it returns. The ABI tells us how we can use a contract. And actually, we can just generate both of them at the same time like this, solkjs-bin -abi counter.sol. Let's take a look at the ABI. And that's a bit compact, so I'm going to pipe it through JQ for indentation and color. Reading this ABI, we see that we have an array with one entry for each function. Here we have get, which has outputs of a uint256, our increment function, and our constructor. We'll use this ABI when we call our contract as an object. Let's flip back to Geth and deploy this contract. First, start Geth like we did in the earlier video. /bin/geth, pass the datadir, and call the console. Now we're in a JavaScript console, so we can declare variables, functions, etc. As a reminder, in an earlier video, we created some accounts and mined some ETH. We'll need both the accounts and the ETH now, so if you don't have those, go back to that earlier video. The first thing that we're going to do is assign our contract hex code to a variable. It will help if you have two tabs open. I have a Geth console in one and a shell in the other. So I'm going to cat counter sol counter.bin. And here you can either select to copy and paste the code, or because I'm on a Mac, I'm going to use pbcopy. And flip back over to our Geth console, we'll create a variable, var counter code equals, and then paste in our code into a string. Let's take a look. Now, to create an instance of this contract on the Ethereum network, we need to send a transaction. Also, to send a transaction, it will cost some ETH, so we need to unlock our account first. Now it's time to send our transaction. We'll type eth.sendTransaction from ETH account 0, and for data, we're going to pass our contract code. But hex strings must be prefixed with 0x. So we're going to prepend our counter code with the string 0x. For the third parameter, we're going to set gas. We haven't talked about gas yet, so just put 1 million here. The second argument to send transaction is a callback function, with the first argument being an error if there was any, and the second argument being the transaction. We'll just console log both of those out. Notice in the output that we have contract equals a hash. This hash is the address of our contract. This is a permanent address, so make sure you save this value. We're going to need it. Here, we'll set it as the variable contract adder. One way we can check on our contract is using eth.getCode. Here it says 0x, which means something isn't right. And the problem is, although we've submitted a transaction, we haven't mined it yet. So let's mine it now. This might take a second. All right, we'll stop the miner. Let's check eth.getCode again. Great. If you call eth.getCode and it says 0x, then something went wrong. A value of 0x means it didn't work. But here I can see my contract code, so we're good. We've deployed our contract. Our code's permanent address is now stored at the value of contract adder. You can think of that address as your contract's personal domain name. It isn't pretty, but it's uniquely yours. Now that we have a contract on the blockchain, we can start using it. To do this, we're going to make a JavaScript object that acts as a proxy to our smart contract. Remember that our contract code doesn't describe its own API, so we need to use our ABI file. The process to get a handle of our contract instance feels a little odd coming from normal JavaScript. It looks like this. First, we'll parse our ABI into a JSON data structure. Second, we'll create a contract class using that ABI. And third, we'll instantiate that class using our address. It's probably easier just to show you in code. First, we're going to copy our ABI definition file we compiled earlier. Next, we'll go back to Geth and parse the string using json.parse. Take a look at the ABI. You can see that it's an object. Next, we're going to create essentially a JavaScript class for our contract. var counter equals eth.contract, passing the ABI. And finally, we need to tell our code where to find this particular instance of the counter contract on the blockchain. So to create an instance, we type var counter lowercase equals counter at the contract address. And looking at counter, we can see we have our address and our functions get and increment. Now we have a handle to our contract instance in JavaScript. And this means we can now interact with our contract's code like a JavaScript object. Sort of. Remember that all reads can be performed locally for free as long as they don't change any state. Let's try to use our read function get. Do you remember what the return value should be? Great, it's 1. We just read our first value from our first contract on the blockchain. Even though we just read a single number, it's worth noting that right now we have the pieces that we need to build JavaScript applications that read any data from the Ethereum blockchain. We'll talk about how to connect this to the browser using Web3 in a bit, but by making this connection between Solidity and JavaScript, we're now in somewhat familiar territory, for a minute anyway. It gets more complicated when we want to update the state. Let's call our increment function now. Counter.increment. Error, invalid address. Well, it might not be clear what that message means, but it's clear that what we were trying didn't work. And the primary reason is that you can't just call functions that change smart contract values locally. You have to submit a transaction that the rest of the network agrees is valid. So how do we do this? Here's another area where Solidity JavaScript API is not that intuitive. To send a transaction on a contract method, we call send transaction on that function. It looks like this. And you might need to unlock your account again. We'll call counter.increment, but then on that increment function, we'll call .send transaction from ETH account 0. So here we're calling the send transaction function on the increment function. This API of calling functions on functions to change their behavior is something we'll see a few times when using JavaScript and Solidity. Our send transaction call returned the hash of our transaction, and notice that the recipient is our contract address. And what will happen if we call counter.get right now? You probably already know that we need to mine another block first, so let's do that. Miner.start, miner.stop, and now let's call counter.get. 2. It works! We wrote our first change to our contract state on the blockchain. Now, if it didn't work or you want to dig in, you can use debug.traceTransaction and pass the address of the mined transaction. You can also call eth.getTransaction or eth.getTransactionReceipt. This might output quite a few logs, but you can just check for any errors for now. Of course, this is a simple contract with a simple application. The next thing we're going to do is bring the interface to this contract into our web browser. In the last video, we built a simple counter contract in Solidity. We deployed it to the blockchain and called methods on it to update the state. There's a lot more we have to learn about Solidity and smart contract programming, but I want to show how to make a connection all the way to our web browser. That is, I want to make a user interface for this contract. I think it's helpful to see how an Ethereum-based app is done end-to-end, and then we'll go back and learn how to make more sophisticated apps. To build a UI for our Ethereum app, the key idea is this. Our Ethereum node has a JSON API, and we'll connect our browser to that API. So the core architecture is that we have an HTML file, which loads JavaScript. And this JavaScript, instead of calling out to, say, a normal centralized server, will call to our personally controlled Ethereum node instead. Now, just to be clear, our web app is all just JavaScript. So you can call out to other servers if you want to, just like you can call lots of APIs in a normal JavaScript app. In fact, this really is just a normal JavaScript app. The only difference is that we're connecting to an Ethereum node for the API. The library that we use to connect our JavaScript code to the Ethereum JSON API is called Web3. To build our UI, we need to start with a basic HTML, CSS, JavaScript boilerplate. I'm not going to teach web development here. We have other books and courses if you want to learn that. Instead, I'm going to assume that you know how to write JavaScript, install NPM modules, and use promises. In a real app, I'd probably use a web framework like Angular or React, but I want to focus on what's new here, and so vanilla JavaScript will be fine. I also want to warn you that in this tutorial, we're going to take some JavaScript shortcuts, like creating global variables on window and directly manipulating the DOM. We'll cover how to properly structure larger Web3 apps later, but for now, let's just get it working. Everyone has their own favorite boilerplate, and I'm going to use NWB here, because it's an easy way to get a nice vanilla JavaScript app up and running. So we can install it first by doing npm install -g nwb, nwb new web app hello counter. Then I'll cd into hello counter, do an npm install, and then I'm going to npm install web3. We can start our server using npm start, and then open localhost 3000 in our browser. A great thing about this configuration is that it will automatically reload our app whenever we change these files. We can open up the code and see that the basic app we're given has an index.html and an index.js. The first thing we'll do is require Web3. And the way the Web3 API works is we're going to call new on this object. So we'll declare a lowercase web3 equals new web3. And so we can expose variables to our console by setting them on window. So let's make web3 accessible to our browser console by typing window.web3 equals web3. The next thing to do is to set the web3 provider. In this case, we're just going to use the HTTP provider, but you could also use WebSockets if you wanted to get real-time updates. And notice that we're setting the address to localhost port 8545. This address is the address of our Geth RPC server. We haven't booted Geth in an RPC mode yet, so let's do that now. Flip back over to our Geth shell, kill it using Control-C, and let's start it with new options. So I'll use bin geth datadir. I'm going to set the options no-discover, RPC, RPC API, and then a list of RPC APIs that we want to use. DB, personal, ETH, net, Web3. There's several. These are the ones we'll use for now. And then there's a few other options. RPC cores domain, you don't need to worry about that for now. RPC address, I'll put localhost, RPC port 8545, and console. You can find this full command in the lesson notes. Feel free to adjust the RPC address or RPC port if you need to. For example, you might try using 0.0.0.0 for the RPC address if localhost doesn't work on your machine. You might also need to change the RPC port. But essentially what this will do is launch Geth in console in our shell, but it's also opening up an RPC server in the background, which our web browser can connect to. Now we should be connected to our Geth node. We can try it out by typing web3, web3.eth, web3.eth.personal, and web3.eth.personal get accounts. Now notice here when we call the get accounts function, it returns a promise. So if we want to actually get the result of our accounts, we'll type web3.eth.personal.getAccounts, and we'll call .then, and then we'll log out the results of that promise. If this didn't work for you, check out the network pane in your browser. But at this point, we should have Web3 connecting from our browser to our Geth RPC server node. Now what we want to do is write a button on our page that will allow us to check the balances of our accounts. We'll do that by writing app.innerHTML equals, and then we'll put an h2 tag to show some text, and then a button where on click we're going to call the check balance function. Now let's write a function that will check our account balances. Again, it's not a good practice to put functions on window, but we're just testing Web3 here. So we'll type window.checkbalance equals function, and first we'll call web3.eth.personal.getAccounts.then. We'll log out those accounts, and then we'll get the balance of the first address by typing web3.eth.getBalance account 0. That also returns a promise, so we'll call .then and log out the balance. Let's flip back over to our browser, try it out. Great, there you can see that we checked the balances of our Ethereum accounts in our browser. Now that we know that we have a connection between our browser and our Ethereum node, let's make a connection to our contract. Remember that in order to create a JavaScript representation of our contract, we need to load the ABI. Let's copy the ABI that we compiled earlier into this project. Only I'm going to rename it to have .json at the end. So I'm going to rename it to counter sol counter ABI.json. In the code, we can use a JavaScript require to load this .json file. This is possible because of the nwb config. If you're building using another method, you can always just copy and paste the ABI here in the code. I'm going to type let counter ABI equal require, and then I'm going to require the file. We can log it out to make sure it loaded. See it in the log. Great. Also remember that our particular instance of the counter contract lives at a specific address on the blockchain. I hope you saved the contract address from last time. So I'll copy that address, and I'm going to define a variable, let contract address equal, and then paste the hash in. And remember, this is an important point. When you deploy your website, it lives on a specific domain name. when you deploy your contracts, they'll live at a specific address. So you'll have these addresses hard-coded, or at least in a config file, committed into your code. So now that we have our ABI and our contract address, we can create a new contract object. We do that by saying var counter contract equals new web3.eth contract. We pass the two arguments, counter ABI and contract address. Let's assign this to window so that we can inspect it in our console. So looking at counter contract, notice that the functions that we want to call are in methods on this object. In order to get the value of our counter, we have countercontract.methods.get. But notice here there are two important functions on get, send and call. There's a difference between them. We use call when we want to call a function locally, and send when we want to send a transaction to the network. Getting the value of the counter can be done locally, so let's use .call. However, calling out to our Ethereum node is async, so .call will return a promise. So we call countercontract.methods.get.call.then, and we take the count and we'll log out the count. Great, we got our count. Now let's add a function for this and show the value in our view. First thing we'll do is we'll add a div and placeholder to show our counter value, and we'll update our button to call check counter. Let's define our check counter function. First we'll type window.checkCounter equals function. Then on the contract, we'll call countercontract.methods.get.call.then, which will be given a count. Then we find the counter value element by ID, and we set the inner text equal to the count. Flip back to our browser and let's try it out. Great, it works. The next thing that we need to do is send a transaction from our browser to mutate that counter value. Now let's mutate our contract state by incrementing the counter. To do this, we'll need to send a transaction to the blockchain. We can check this out in our console. The counter contract object has functions that help us build this transaction. It looks like this: countercontract.methods.increment. We'll call .send on this. .send means send a transaction. So recall that to send a transaction, we need to specify the sending account as well as the amount of gas that we're willing to spend to run this transaction. Let's grab our first account address and try it. We'll set our account to a variable, and then call countercontract.methods.increment.send, passing from our account. Gas, we'll just put 1 million. .then, and capture the error and the response and log it out. The promise that returns isn't resolving. Let's check our logs to see if we can figure out why. In the network tab, we can see the response that says authentication needed, password or unlock. We forgot to unlock our account. So let's do that first. We'll type web3.eth.personal.unlockaccount, pass our account address, and then the password ABC123. Looks good. Now let's try resending our increment transaction. Looking at the network tab, it looks like it went through. Let's mine this transaction. Back in Geth, we'll do miner.start. Got our transaction, and miner.stop. Let's check our counter again. It works. All right, let's add a button which will increment this counter for us. We'll set our from account. So we're going to add a new button where onClick calls increment counter. And let's define our increment counter function. We'll call window.incrementCounter equals function countercontract.methods.increment.send from account gas 1 million. And let's flip back over to our browser and press the increment counter button. And we need to mine the transaction. Now, I don't know about you, but I'm getting tired of starting and stopping the miner manually. So let's just leave the miner running. Now let's increment the counter. And if it doesn't work, you might need to unlock your account again. Let's wait a couple seconds for it to be mined. Then check the counter value. It works. Let's try that again. Wait for the miner. Click it again. It works. Fantastic. So there's a really basic Web3 Ethereum tutorial. I think the most obvious improvement I'd like to make here is to have the counter value automatically update in the view once the transaction has been mined. We'd use WebSockets to push the new information from the RPC server to the browser, and then we could update this value automatically, without the user having to check manually. But using WebSockets is something we'll cover in a later video. In fact, we have a lot to cover in other videos. This tutorial shows you the key connection and how to build dApps, but there is so much more to cover. For example, I want to talk about the specifics of writing real-world Solidity contracts, taking performance and security into account. I want to talk about building apps where our users can trade collectibles, or vote on resolutions, and make provably fair agreements. I want to go beyond Ethereum and talk about distributed storage with IPFS, and talk about high-throughput transactions with sidechains and state channels. I want to talk about how to accept Bitcoin payments on your website without any bank or credit card intermediary. And of course, we're going to talk about how to build your own cryptocurrency. We'll discuss what it means to create your own tokens and how to integrate them into your own apps. For now though, let's celebrate our success connecting our Ethereum network to a browser app. We're entering a brand new world, and we've got a lot to build.